You have requested it, and I am willing to abide. Let's do an example of determining the order of reactants in order to determine a rate law for a reaction. So this is chapter 14, and I pulled a sample problem 14.34 from our book. And as you can see here, what they did is they chose a situation where what we can do is, in order to determine the reactant of one, you have to keep it constant with the other. So if I want to determine the order of reactant for ClO2, for example, I want a situation where these are changing, but these are kept the same. So in order to find ClO2, I'm going to use, I may have set myself up a little over here. So in order to find, and I need to find letter M. So in order to find M, right, I can compare experiments number 1 and 2 only. So if I were to compare experiments 1 and 2, let's do this the long and hard way, shall we? This is the reaction. This is a reaction. This is a rate of reaction equation expression. So rate is K, which we will determine in the next video. This is part 1. K times the concentration of one of the components to the power of its order of the order of reaction, of the order of the reactant, times the other component times its order of reactant. So we need to find this exponent here. So how do we do that? Compare 1 and 2 to find the one for chlorate, because, or chlorine dioxide? Okay. We have to compare a reaction where these are kept constant, right? So what we do is we say, okay, here, what we do from 2 to 1 is, what do? We triple it. And what happens to this? So let's do the long and ugly version of it. So the rate, I'm going to put 2 over 1. How about that? No, let's do 1 over 2. Let's do that. So I'm going to compare rates 1 and 2. So this is experiment 1 and experiment 2. I'm doing the long and difficult version way so that you understand where it comes from. So I'm going to fill this in with what I know. What's the rate for experiment 1? 0.00276. What's the rate for experiment, oh sorry, I mixed it up. Woo. This is live, people. The rate for experiment 1 is 0.0248. Experiment 2 is going to be 0.00276. The K, remember, K is a little lowercase k, and he's the same in both situations. So it doesn't matter. As long as your temperature is the same, you can vary concentrations, and K will be the same. So what's the concentration of my ClO in experiment 1? 0.060 to the power of M, which I don't know. How about in experiment 2? 0.020 to the power of M. I'm not sure what that is just yet. And then it's multiplied by concentration of OH, which is 0.030 to the power of N times 0.030 to the power of N. So what do we notice here? This is where all of our, we got to kick our brains in overdrive here and go back to algebra. K is going to be the same no matter what, correct? So dividing K by K is redundant. How about whatever N is, it could be 0, 1, or 2, we are having the 0.030 to the power of N. So this term is redundant. So my new equation is actually just 0.0248 divided by 0.00276 equals 0.060 to the power of M over 0.020 to the power of M. Now if we go back to algebra, First step, we can make that left side look a little less hectic, right, by going 0.0248 divided by 0.00276, and that is 8.99, and that's going to equal, so then what we do here, which is what's 0.060 divided by 2? That's actually 3, right? And you could put that in brackets to the power of m. Now what could 3 to the power of m be and essentially be 9? We're going to call this 9. 3 to the power of 2 equals 9. Now why isn't this like a perfect number? The answer is because, you know, labs are flawed, experiments are flawed. So your number might give you 8.99 and you can assume that that's 9. Remember, these numbers have to be whole numbers. So what is my m? 2. So we just found that m equals 2. So how can I make that look special? How about m equals 2? Right? So we can conclude that m equals 2, maybe double box it. Yay, we found one order of the reactant. How about the other one? Let's see if we could just visually determine it. So in order to find the order of reactant of hydroxide, we're going to have to find a situation where these change and where these are kept constant, the other reactant. So if you're playing at home, it's got to be 2 and 3, right? So it looks like between 2 and 3, these stay the same. So very much like our mess down here, they would cancel out, correct? So what happens here? We triple it. So this divided by this is 3. So let's do a little math. What is this divided by this? So 0.00828 divided by 0.00276. Tripled. So, rule of thumb, if what you do to the reactant happens to the rate, the order is 1. But if we wanted to see that written out as if we fast forwarded to the final step here, so if we wanted to find n, messy, you would say that it is essentially 0.090 to the power of n divided by 0.030 to the power of n equals, and then in our calculator we typed it out, it actually equals a perfect 3. So I'm not going to type it out because I guess I'll write it out. 0.00828 divided by 0.00276. So sorry about the mess here. But this is going to equal 3 to the power of n equals 3. So what should n be? N has to be 1. So n equals 1. Gorgeous! So we can actually rewrite this equation up here. K, concentration of ClO2 to the power of 2 times OH minus concentration. We can write the 1 if we feel like it, but it's actually not necessary because we determined it to be 1 and you typically don't show that. So keep an eye out for part 2 where we finish it up and determine the last variable, because remember, I'll circle them with reds. In order to write a full reaction, a full rate law, you have to determine K, and you have to determine the order of each reactants. All right? So keep an eye out for part 2. Thanks.